You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technology specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. Laurent Fokel is a field application engineer and a global business consultant with Worth Electronic in Germany, and he has been in the business for many years. Now, you might recognize Laurent from one of his many presentations around the globe, or even his cartoon avatar from the Ask Laurent videos available at Worth Electronic online. Today's podcast comes directly from a recent webinar presented by Laurent, where he discusses EMI problems designers face on the PCB level. How can a developer solve EMC problems on the circuit board or prevent them from occurring? What has to be considered, and where does it make sense to use a filter? Which system impedances are there, and what are the deciding factors for which filter topology should be used? Laurent answers these questions and will show us how to correctly use a simplified filter calculation for a switching regulator. Enjoy today's presentation of How Do I Solve EMI Problems on PCB Level with Laurent Fokel.
In EMC, you have some requirements which you have to fulfill. It depends on your location, but in the EU, you have 20 regulation and directives which you have to fulfill. One is the low voltage, the other one is the EMC. The RED, radio keypad device, are already included, the EMC. Then you have some machinery directive. Of course, there are also different medical and military directives as well, but I will focus on the industrial EMC compatibility. Different countries like US, you have to comply with FCC. FCC to the CE marking, it's a little bit different. The FCC doesn't care about immunity. You have some different frequencies sometimes and different levels. If you are selling something to Japan, you have the VCCI. In Australia, you have the CETIC. In China, you have CCC. Every country you will find EMC regulation. It's very important of economical point of view when you start to design the EMC conformity, because when you think about the EMC issue and you are design your device and you want to start mass production and you go to the EMC lab and you realize, oh my God, I'm not passing the test. It's very difficult because you have to redesign and you have to invest money, you have to invest time. This is not the aiming of the EMC law. Actually, the EMC thinking starts in very early stage in the development. When you're designing your schematic, you have to think about EMC already. If you have already made your prototype, it's maybe too late. I just consider always the EMC before I start my PCB design. So this is very important because you can make almost 80% wrong before you start your PCB design. And everybody wants to pass the EMC test very fast and very easy. How you can check the EMC? This is the biggest question and many times asked. How can I check the EMC? Well, this is not so easy. To check the EMC, you will need something like an EMC anechoic chamber. This is absorber room. You need antenna, you need receiver, and you need also staff who can handle these machineries and make the right measurements. So the investment is very fast for an EMC pre-compliant test, something like 500 million euro. So not everybody have this luxury to have our own EMC chamber and have own EMC setup. Some pre-compliance tests could be done with less than 100,000 euro, but you have to make anyhow some investments. The most important thing, which is sometimes forgotten, that if you have different source and load impedances, you have to use different filter topologies. I always start with the LC filter, then I see that the LC filter doesn't work like I wish. I give them a second capacity. I make my P filter. If I see that doesn't matter how I change the capacity value, it's still not giving the right filtering effect, I go back to my LC and give a second L. So I did done now a T filter. One of those filter will act excellent for filtering a differential noise. For capacity, I suggest to start with small values. Start with 1 nano and go maximum to 1 microfarad. With the inductor, it's very important that you're using inductor which is for manufacturing made already like a choke. It should be not always a good storage inductor. It should be a filter inductor, so choke which has very low Q factor. The Q factor definition is the impedance reactance, XL, divided by R, the losses, not the DC losses. Pay attention about the self-resonant frequency of the components to don't build another EMC problem. Where are the EMC noises? Who are responsible to make this EMC noise? Well, in fact, it happens like if you make a buck converter. In the buck converter, first of all, you have here a switch, you have here a second switch, you have a storage inductance, output capacity, input capacity. It means you're going from a high voltage to low voltage. And first of all, what you're doing, you charge your input capacity with energy, and through this switch and coil, you transfer this energy into the output capacity. So actually, you have to, sorry, excuse me. You have to take care because this path, the input capacity ground to the output capacity ground, this PCB track is your most radiating antenna because you transfer energy from one cap to other cap, and actually this is a dipole antenna here. If you take a near field probe and you go close as possible to this path, you will see that is the most radiation area. So keep this track short as possible, low impedance as possible, and don't route it on different level. I always say never press the auto routing button because this auto routing button on the PCB layouter, I will rename it like make EMC problem button. Additionally, you have to take care about the output as well. You will have a buck converter, high ripple on input, and you will have some rest ripple on output. But the most important by buck converter to filter the input. Now, if you look on these noise loops, which is happening on the converter, you can see that you have a quite big area and a quite big loop here when you switch on and this is a synchronous buck instead of using a diode. It's again a MOSFET. And you can see this loop is the most dangerous area because you have a high DI after DT in this area. In a B loop, you have a shorter and mostly a very small area where you're pushing energy between inductor and capacity and you take it out to the load. But this is the most dangerous area. Try to be aware about this area, and also your feedback, try to go away from this noisy area because your feedback is also sometimes self EMC problem generated because of your high DI after DT. Now, if you look on your input capacity and your input tracks, you also realize that the input capacity is not the ideal capacity. The input capacity has, of course, also some parasitics. He has a ASL, he has a ASR, and all this together with the input line, you generate again here for from the source, which is also capacity, input noise area, which can be done, and you will have this area which will radiate, or you will have this problem because conductor emission. By the output, you have to take care about the output capacity again. This is not the ideal component, and your load. And again, you have to take care about this small output noise. For a buck converter, it's not so difficult, but for a boost converter, it's definitely, this is the area for the boost where you have to pay attention. A boost converter is not so aggressive on input, but is more aggressive at the output. Now, if you know exactly the ASL, ESR value, which you can read it from the datasheet of the input capacity, and you can estimate your parasitic sum, your input wires, input tracks, with a very simplified formula, you can already pre-calculate what will be the expected noise on the input. Additionally, you look on your scope and you realize that even when you are switching just at 500 kilohertz, you see some noise at very high megahertz. And this is the harmonics and the high frequency issue which is generated in this area because the diode is not ideal and the capacity is not ideal. You may have a resonant frequency circuit here on very high frequencies. You may see this overshot and ringing, which is happening in this area. Again, try to keep these tracks short as possible between the storage inductance, output capacity, and the back track, the back path to the diode. And if you can use a synchronous buck converter, instead of using a diode, use a MOSFET, you will see that the overshot will be less and the ringing will be much, much less. Additionally, if you use an output MOSFET from controller, is not a chip which has the MOSFET built in, you have to think about this pad where you are sending these digital signals to the MOSFET and you are making a back pad to the IC where you can generate a big loop antenna. Be aware about that. This is not the best way because you have a digital on-off signal or very rectangular signal. It's a digital signal, and you have to take care about this path of these data lines because actually this is like a data line, and you have to match the impedance and make them short as possible. And the best thing what you can do, you can put, if you have 2-layer PCB, 1 layer on the top to the MOSFET and 1 layer back to the controller and float with ground on left and right hand also on the top and make small vias, and you can close this area in kind of semi-shielded area. I think I talked to many people about EMC, and I realized that many people confirm that you can make a new definition of an AMI noise formula. This is not a really mathematic formula, but you can tell them the noise field. It is depending on current multiplied by the loop area of the current which is flowing, multiplied by the frequency which you're using. Because as more current you have, as more magnetic field you generate. As larger loop area you will have, as bigger will be antenna, as larger will be the field. As higher frequency you're switching or you're working on higher frequency, as higher will be the harmonics and the noise. So this is a kind which you can already think about. Some people say, the shortest path is the best thing to do it. But keep in mind, the shortest path theory, it's correct, but you have to take in consideration the enclosed area. It may generate a short path, but you will have a large area, which again, it could be the area which will emitting. Remember, current multiplied by area multiplied by frequency. So if you change instead of the short path and you are doing on your routing a small trick and you reduce this noisy enclosed area, it may generate maybe a small delay here, or it will be not so good matched the impedance, but your area will be smaller, and then automatically your EMC will decrease or will be disappear. That's keep in mind sometimes, because I was in mind always the shortest area, the shortest path is always the best path, but sometimes you have to consider also how much is the enclosed area of this noise. How to make a good filter design? Well, if you have a DC-DC converter, the most important thing is that you have an input capacity, and this input capacity will have a ripple from the input. So what you can do for the third harmonic is something like you can put here a small inductor. This inductor cannot be millihenries, because when it's a high millihenry inductance, it will slow down the current flow and your capacitor on input, maybe it will be not charged in time and he will die hungry. So you have to take care about this inductor, that it should be a value between 1 microhenry to maximum 10 microhenry. Very, very rare I use something like 22 microhenry for very low switching. But normally it's a low value here, which is responsible actually for the third and sometimes even for the fifth harmonics. Now, how to calculate this inductance value, because I don't want to lose my efficiency. Well, if you design something today, I would say a minimum efficiency of 80% will be required. If you take this very simplified, easy formula, output input report multiplied by the current divided by the efficiency, and you have, like in this example, an input voltage of 20 volt, output voltage 5 volt, output current 4 amp, and you aim for efficiency of 80%, and you put in this formula, you may have on this inductance 1.25 amp. Now, it's very important that at 1.25 amp, which will flow through this inductor, and you want to have this 80% efficiency, this inductor and that value, it should be not saturated and it should be not hot. How to find out what is the saturation point or the linearity of this inductance is quite very easy. You can open our website, which is offering this software-based RedExpert website. And if you go to this web page, RedExpert, this is our online RedExpert, you can very easily find out for the inductor if it's saturated or not saturated. I just choose now one example here, like a buck converter like this, and I would choose just to calculate the inductance for a simple buck converter like 10, 12 volt to 5 volt to 8 amp, and I will leave 500 kilohertz, maybe not 500 gigahertz, will be too early for today, but I will calculate the inductance value. The inductance value is say 2.60 microhenry. Now 2.60, I can choose this one. Automatically, as soon you choose this one, you have this inductance versus current. You can see the inductance versus current. So for my inductance, in this case, if is this inductor used for the filter, I want to know that at 1.25 amp should be not saturated. So I can see this is very quite linear. I'm fine with this. I can use this one, no problem. If this is a storage inductance, like in my case, I need like 2.16 microhenry. My output current is 8 amp. I can see at 8 amp. At 8 amp exactly. It's quite very good. It looks nice. I have 2.21, no problem. Everybody love it. But I know that I have a small inrush current when I switch on the engine or something. It could be happen that sometime you have an inrush current, and this DC-DC current will have not only 8 amp, it will be have for short time maybe 15 amp. At 15 amp, I want to see what happened to him. It will drop to 2.13. Now, yeah, 2.15. I'm almost okay, no problem. You think it's a no problem? Yes, that should be like that in the theory. But you know, all the data sheet at every manufacturer is measured in a laboratory condition. It means at 20 degrees Celsius. What happens if I don't have 20 degrees Celsius? What happens if I have minus 40 degrees Celsius? This is not containing the data sheet, but these data are measured and given in RedExpert and are shared this information with you. At minus 40 degree, it will drop the inductance to 2.09. Oh, this is less than 2.16. It means my ripple will start to exceed very high. My inductor will start running quite hot, but I have minus 40 degree. It's not a problem. How about if I have a hot environment like 110 degree? Uh-oh, my inductance dropped much more, and this is something which I don't want to have it. Not that much. I would expect a little bit more much. I did not expect that. This is a very good inductor, honestly. Normally, it should be saturated much better. I choose one of the best one. by accident. So normally you can see as soon you're increasing the temperature, the saturation point is going lower and lower and lower. And that could be that the inductance already highly saturated and at ambient room temperature it's quite working pretty good. But when you have a hot environment and you have this hot start or cold start, like the inrush current, may happen that your inductor is already saturated and doesn't work anymore. Keep in mind all these values are in Red Expert, and you can just download it. You can just get the data sheet, just single click on PDF and so on. And all this information are available, and they are measured value, not calculated value. So let's go back to our filter design. And the filters design, additional, if you want to cut also the fifth and seventh harmonics, I recommend to the L on front of the input capacity, put a second small capacity, a value between 220 pico to maximum 1 nano, low ASR. The best way is a ceramic. You have here electrolytic, you have here a ceramic. And to make them more efficient, you add the ferrite bead. A cheap bead ferrite, a value between 100 to maximum 300 ohm, because 300 ohm is measured in a 50 ohm system impedance, and we are here in much lower system impedance, so his filter effectivity will be much better. Now I have a fifth, seventh harmonics filtering. It's actually a T filter. I have here for the third harmonic plus the input capacity, a varying about the inductance value. If you want to simulate that, even it's possible to get all the libraries are available on the website, and you can simulate with LT-Spice, and you can shift your filter in the frequency where you want to filter it. Now for the output, actually for the buck converter, you don't need to filter too much the output, but in case it's a boost converter, you can mirror exactly the same thing on the output like for the buck converter, and then you can do the same thing in the output for the boost converter. If it's a buck boost converter, sorry guys, bad luck. You have to filter input and output because both will be, depends on his mode. If it's a buck mode or boost mode, it will be need to be filtered if you don't want to generate any conductor emission. All that it is for a differential noise. In case you have a common mode problem, you have to use a common mode choke, of course. But be aware by the common mode choke, I like to use for the DC-DC converter a sector wounded one, not a bifilar, because I don't have data line where I'm afraid about the non-linearity or about the leakage inductance. I want to have this leakage inductance because sector wounded have a high leakage inductance, and I can do with this leakage inductance and additional capacity on front. I have anyway a capacity on after. I have my leakage inductance T filter, and this is work perfect against differential mode, and for common mode I have my common mode choke, and I'm happy to filter also the radiated emission common mode noise if I have long tracks here or long wires here. But be aware, if you use a common mode choke, after you put the common mode choke, you define your ground point. It's not allowed to have a ground connection in front of common mode choke and a ground connection after the common mode choke, because if you have ground and ground connection about the common mode choke, you make a short circuit about this winding, and beginning at that point, if you short circuit one winding of the common mode choke, his function is good for having more heavy material on the PCB. It's good for some more weight, but not for the EMC. Some layout recommendation about when we talk about layout. Layout recommendation is good because you can do many stupid things on the PCB. Like if you build a T filter like that, in fact, according to the schematic, they are correct connected, but a long track for the capacitor and then put a wire to grounding. It's very crazy. Don't do this, please. For the capacity, after you place your PCB pad, the footprint, immediately put a wire. Much better, put two wire. One single wire have 0.5 nanohenry inductance already. You know, if you put two wire, you have two inductance in parallel, and automatically you have half inductance. Automatically you have half resistance. Some people even put 3 wires. If you have the space and it works, why not? About this insertion for high frequency, well, we can start a discussion. You don't need to do that if you don't want to filter gigahertz. By gigahertz, you will see in every RF module the capacitor using that. For high gigahertz frequency, it's neat because else the gigahertz will shut away by that. But don't do a long track to the ground from here. If you use a commode choke, this is also a design from one customer who made some not the best thing routing. He put noisy area here, capacity, commode choke, and then track back very close to these tracks. Actually, the noise was not so well filtered because it will jump from one track to other temp and you will contaminate again the filtered area. Redesign was not so helpful because again he did not consider this PCB track distance, and this could be again make some problem, and actually he failed with that. He failed with that by air soldered solution. I was on the measurement. He did passed. As soon as he put on a PCB, he lose the EMC norm and he was out of the limits. And then after the third redesign, making the PCB tracks like that, you have the noisy area, you have the kind of creepage distance like for the transformer, you keep away the noisy area from the clean area, and beginning from that point, he was happy that he will pass in the EMC test. What is the big difference between a shielded and unshielded inductance? Again, it's a big difference. First of all, it's a different additional material around the bobbin core, which is here on the storage inductance. You can see here, it's also bobbin core. If you make a magnetic cut in the middle, you can see the shade of the core. This is the wire, the highest magnetic flux. And if you put around this bobbin a shielding, it may happen that this big magnetic field will not breaking out so strong. You may have a small gap on the top and bottom, but a huge magnetic field is turning back using the wall of this shielding. And that makes that the DC-DC converter will not radiate using unshielded inductance. Just to remember, I made here with some colleagues some tests in our EMC lab without putting the limits of EMC low regulation, measuring conductor emission 150 kilohertz to 29 megahertz, and using a DC-DC converter, switching frequency 2 megahertz, 1 amp output. We use an unshielded inductor. We put some marker to the peak measured in conductor emission on output from the listen, and then we take a soldering iron and desolder the unshielded inductance and solder a shielded inductance. Now you can see 90 dBm much better. You can see here it's much better, the EMC for conductor emission, only because you use a shielded inductance and not contaminate the system. In the EMC chamber, radiated emission, I think the pictures speak from himself. If you use an unshielded inductor for storage, it will radiate. If you use a little bit more, maybe 5 to 10 cents more expensive shielded inductance, you don't have to pay additional €5 for the snap-on ferrite on the cable because it's already decontaminated and keeping the magnetic field quite strong on the inside. Another experience from a customer, double-side PCB, a motor controller. He used here 2 inductors unshielded. He passed not the conductor emission, he failed. It was quite noisy. We tell to him, change this inductance to shielded one and float the empty space here with ground. This is also good if you have so much empty space, floated with ground and put some via. You go back to EMC lab, restart the measurement, and the EMC guy start to be nervous because he doesn't want to believe that such small change can be such big impact. The bottom line is the noise floor of the measurement EMI receiver, and you can see you are just scratching the surface a little bit above the noise floor. So before and after, just because changing the layout, of course, and changing the inductor to be shielded version. Like I told you, in Red Expert, you can get all this information for all the inductance. Additional, you have the core losses, which is not using Steinmetz formula. We have our own algorithm, our own formula, and we are 99% accurate. We can have core losses and proximity effect losses, and also skin effect losses included in our calculation, and this is measured values as well. With the thermal camera about the temperature rise, you will have always exact value for your real application. Steinmetz formula cannot use like example for iron cores or different core material mixture. In our example, in our Red Expert, you can have different material, and always the formula is valid and is always 99% correct. Even you have not 50% duty cycle like by Steinmetz, you can have also different duty cycle. This is also considered. If you use TI Webbench software as well, there's a link. If you will download the PDF, you just have to click on that and you can start automatically the Webbench. We are also here listed and also in different development boards. Our conductor are on it. For LDSpice 7, now is the 7th version on released, I think last year, and you can even have impedance DC BIOS with DC BIOS load. This is unique for virtual electronic. We did make a lot of measurement and special fixture made to have a good model about the DC BIOS saturation for, like example, chip-bit ferrite bits. And you can see this is in datasheet, and this is in reality when you pass with a big 3 amp current through a 0603 ferrite bit. This information again is in LTSpice. You can download the model from our website, or sometimes it's already included.
This podcast was taken from a popular Worth Electronic webinar. To view the materials and replay the webinar on demand, visit www.we-online.com/webinars or click the link attached in this podcast. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.